Today our topic is cosmology. Cosmology means the study of universe. Very simple. After that, you should know what is meant by luminosity. Luminosity. For example, here you have a voltage source AC and here you have a heater. So as soon as the alternating current will pass through it, what will happen? It start giving off radiation. So this is total power output of radiation given by a heater. For example, this is a heater. Now if you are standing here, then this radiation you will receive as well. Now here, how much radiation you will receive, or power. Keep this concept in your mind. So what is meant by luminosity now? For example, this heater is represented by a star, and this star is giving out radiation in all direction. So here we have to assume that the star will give radiation that spread out uniformly through a sphere of radius r, for example. So this, now star is giving radiation all around in all direction. So total power output of radiation emitted by a star, this what we call luminosity. So this is a total power output. So as it is a total power output, so we can measure in watt, and watt is equal to joule per second. So luminosity is denoted by L, and it is also equal to energy over time. So as I told you earlier, for example, the radiation that are emitted by a star, they spread out in the form of through a spherical shell. So the radius r of the spherical shell, it will increase with respect to time. Yani as you are moving further apart from the star, the radius start to increase. So for example, here is r, this will be a sphere of radius 2r, this will be a sphere of radius 3r, and this will be sphere of radius 4r. Okay, now Earth is present here E, and it is at a distance 4r from the center of the star. As we know that the spherical shell through which the radiation of the stars are distributed uniformly, it keep on increasing, and at this distance the energy emitted by the star is supposed to be decrease. So in the beginning, the more energy, so smaller wavelength, then the passage of time, the wavelength start to increase. And this relation we can know from here, E is equal to hc over lambda, where E is energy. As energy is decreased, so wavelength of the radiation start to increase. Now we have to define a new term, this what we call radiant flux intensity. Oops, we have to write here T. What does it mean? It means power per unit perpendicular area received on Earth's surface and it is denoted by F. If you would like to calculate it, so we have to apply the rule power over surface area. Surface area of this shell, because the earth is supposed to be present here at a distance 4r from the center of the star. So what will be its unit now? Unit will be watt. Unit will be watt per meter squared. As we know that watt is joule per second, so the unit will be joule per second per meter squared. Now, if you would like to derive the formula for it, you have to write F is equal to power is equal to luminosity of the star, which remains constant, and surface area of this sphere 4 pi d square. D is equal to 4r to 4r in this case. So this is the formula in order to calculate radiant flux intensity. F will be radiant flux intensity, L is luminosity, and D is the distance between the center of the star and center of the earth. Inverse squared law, what does it mean? Inverse squared law of flux. As we know that radiant flux intensity is equal to L over 4 pi d square. L luminosity constant and 4 pi is also constant, means whatever the star is there, its luminosity remains constant. The intensity of the output power, it will decrease only, yani the intensity of the radiation will decrease as they are moving further away from the star. So this will be constant. So if it is constant, it means radiant flux intensity is inversely proportional to square of the distance between the object which is receiving radiation. For example, here you have a star, and I suppose that this is a sphere of radius d, and here you have earth. So this radiant flux density intensity, I mean, it obey inverse square law. What does it mean? It means, for example, if you have a star here and this is the radiation released by the star. So if someone is present near to the star, then it will receive radiation flux density in an area R. For example, this is the case. We say that D is equal to, for example, R. If you move further apart, for example, D is equal to 2R, then what will happen? This area, it will divide it into 4 parts. Yani radiant flux intensity, it will divide it into 4. If it is here F, then here it will be F by 4. So if it reaches at a distance D is equal to 3R, then what will happen? The radiant flux intensity, it will divide it into how many areas now? It will divide it into, for example, 9 areas. And how it will be? 1, 2, and 3. 9 areas. 1, 2. So here it was receiving unit area, here 4 areas, and here 9 areas. So radiant flux intensity keep on decreasing. So if you would like to plot a graph of it, then here will be D in meter, and radiant flux intensity will be F, Weber meter minus 2, we know that here this is watt, watt, and meter minus 2. This is the unit for radiant flux intensity. Now, here it is constant. For example, if you consider this area, till here it is constant, and after that it start to decrease. So for example, a distance equal to r, it is constant. After that it start to decrease. How it will decrease now? For example, here it is f at a distance, for example d is equal to 2r. Its value decreased by a factor 1 by 4. Then if it is at a distance of 3r, then its value is decreased by a factor of 9. So this is shown here, constant, then by 1 by 4, then 1 by 9. Also you can write here f is equal to L over 4 pi d square. So if you substitute here, put, for example, d is equal to 2r, then what it will be, f is equal to 4 L over 4 pi d is equal to 2r to 2r square. So if you substitute here, for example, r, 4 pi r square, then what it will be, L over 4 into 4 pi r square. So this is the new flux, radiant flux intensity, f over 4. Similarly, you can prove f over 9, f over 16, f over 25. So it will. So if you are moving away from a star, then flux, radiant flux intensity start to decreases. So here a sphere of radius, for example, r, and here will be 2r, then here will be 3r, and up to so on. Secondly, if you are going to plot a graph between 1 over d square unit m minus 2 and radiant flux intensity, then in that case you will get a straight line. So if you are looking for gradient will be rise over run, yani f divided by 1 over d square. So what it will be, f d square. Now we know that f is equal to L over 4 pi d square. It means f d square is equal to L over 4 pi. So you can write here L over 4 pi is equal to gradient, and it will be constant. Actually, this line is just like slope-intercept form equation of straight line, and you know that along y-axis, this is y-axis, and here we have x-axis. So along x-axis, radiant flux intensity, slope we have L over 4 pi and into x, and x is what, 1 over d square. And we know that this is y-intercept. So in this case there is no y-intercept because the line is passing through the origin. So this will give us equation of straight line that passes through. So from here you can know that f inversely proportional to 1 over d square. It means if d is larger, then f will be smaller and object is far away from a star. Now what is meant by black body? So black body does not mean something painted black. A black body can be divided into two types. First is a black body emitter, and second we have a black body as absorber. Emitter mean a body that can release all type of radiation, yani all the possible wavelength of the energy released by a body. So that emitter might be a star. So in our case we can take it as a sun. So sun is a black body emitter which can release all the radiation that consists of all possible wavelength. In order to understand absorber, first of all we have to take a, for example, a metal block, and inside it you have a small cavity. So if you would like to take a microscopic view of the cavity, so this is a cavity, and here we have a metal. So a radiation that will enter into the cavity, what will happen? It is reflected forward, backward, and until it is absorbed. So this incident light is absorbed by the cavity. So this is a absorber. So this black body can be converted into a black body emitter. For example, you are supplying heat to it, then it will release the absorbed energy in the form of radiation here. So it will release all the absorbed energy. So these are emitted radiation. So in this way we can deal with a black body emitter, natural sun, and artificial a cavity inside a metal. Although when a light incident on the cavity might be it is reflected, some part of it is reflected, but in this case we will consider that all the incident light that entered into a cavity is absorbed by the cavity, and when you will heat it, it will release the all absorbed light. Okay, now we have to move towards standard candles. And what is meant by standard candles? It does not mean a candle in reality that we have on the surface of earth. It simply means stars of known luminosity. Stars of known luminosity. And there are two very famous examples for them. For example, we have Cepheid variable star, variable stars. And what does it mean? These are pulsating star. What does it mean? It means their brightness increases or decreases over a set period of time. So brightness increases or decreases over a over set time period. So they are just like twinkle twinkle little stars. Sometime they are brighter, yani at a particular time they are brighter, then next after equal interval of time they are less brighter. And second we have type A1 supernova. Supernova means a star that gives off its energy at once, just like it is a suicidal star and it involving a white dwarf. So these standard candle we can use as a distance indicator. So standard candles as distance indicator, yani by using them we are able to construct a cosmic distance ladder, mean we can form the large picture of the universe. For example, if here is a earth, one candle is standard candle is here, other is here, then it is here. So you are able to find the distance by applying rule of radiant flux intensity. F is equal to L over 4 pi d square. So d is squared is equal to L over 4 pi f. Take square root, then you are able to calculate d. D is equal to square root of 4 pi f. So in this way we are able to calculate the distance of different standard candle from the earth, and we are able to plot a distance, the cosmic distance ladder, and it will give us a large picture of universe. Wayne's displacement law. What does it mean? It means you have a hot star and it is releasing radiation. Every star has a maximum intensity, and at that maximum intensity it will release a radiation. So the wavelength of the radiation at maximum intensity is inversely proportional to temperature. So this is what we call Wayne's law, Wayne's displacement law. He said that the wavelength at maximum intensity is inversely proportional to temperature. So lambda inversely proportional to 1 over T. So you can introduce a constant B over T. Here wavelength of the emitted radiation is maximum. It means the wavelength of the radiation at maximum intensity. So here is also lambda max. So if you rearrange it, you will get B, which is equal to constant. This constant has a specific value. Lambda m max into T is equal to 2.39 into 10 power minus 3 meter into Kelvin. So if you would like to plot a graph, then the graph will show a strange behavior. Here will be lambda along x-axis, and here we have intensity, watt meter inverse. For example, sorry, I have to draw again. So what it will be? So it will give you a peak value here, then like this. So this is the peak value, and what you have here, the maximum intensity I max, and the radiation that it will release at the maximum intensity. So we have to label its wavelength as lambda max. So if you decrease the temp, for example, this will occur at particular temperature T. So temperature and wavelength, they are inversely proportional to each other. If you further drop the temperature, then the peak will shifted like this. Again, so see here, for example, if here is 6000 and if you have here, for example, 4000. So if you join all of them, it means if temperature is increasing, then from 4000 to 6000 and T, so wavelength is decreasing. So T increases, so wavelength decreases. So this is what black body radiation curve. black body radiation curve. So Wein's displacement law, the wavelength of the radiation at maximum intensity is proportional to thermodynamic temperature. And this temperature will play an important role, any peak value of the temperature. It will play an important role in order to distinguish between the color of a star. Okay, now here the right hand side of the temperature it obey, yani temperature increases, wavelength decreases, but right hand side of this graph was not explained by classical physics. So it shows a strange behavior, and this part of the graph does not agree with the theoretical physics. So this was the experiment value, the data plotted, the data of intensity plotted against wavelength. So it was later on explained by Max Planck. So don't be afraid if you are considering left hand side of this equation. Thank you. Okay, it represents the black body curve for 4 star. Peak intensity at a temperature of 3000, peak intensity of the second star at a temperature of 4000, 5000, 6000. So this is the cooler and this is the hotter in this case. So hotter, it will release tend to be white or blue, yani, and the cooler it appears to be red or yellow. So if you keep on increasing the temperature, the color of the star turns into right to blue or right or blue, and if you decrease the temperature, then it will be red and yellow. And this trend you can see from here. For example, at a temperature of 3000, yellow red color, very small red color. At a temperature of 4000 Kelvin, all color of the spectrum, but peak value exists in infrared region. Here peak value exists in red region along with all colors. Its peak value is in red region here, so it appears to be red. And that temperature, or at a temperature of 6000, peak value of intensity exists here, and peak value existed in yellow, so it will appears to be yellow. Yellow color will be dominant. Okay, we have to start now. Stephen Boltzmann law. Stephen Boltzmann law. And this law represents the relationship between two quantities. Number one, radius of the star and luminosity of the star. Definition is quite simple. Luminosity of a star is proportional to the fourth power of its absolute temperature. Absolute temperature. So if you would like to write formula, what it will be, L is equal to 4 pi r square sigma T power 4. L we know luminosity, r radius of the star, this Boltzmann constant, we call it sigma, and its value is 5.67 into 10 power minus 11 watt meter inverse Kelvin minus 4. By using this relation, we are able to calculate the estimate of the radius. So how we can estimate the radius of a star? For example, we have to make subject r L over 4 pi sigma t power 4. So r is equal to, if you are taking square root of it, r will be, r is equal to 1 over 2t square root L over pi sigma. Now L can be calculated by applying the formula of radiant flux intensity, that is F is equal to L over 4 pi d square, where d is the distance between the earth and the star, or between star and that object from at which you are measuring radiant flux intensity. So L will be F 4 pi d square. Secondly, if you would like to calculate the temperature you can calculate by Wien's displacement law, 2.93 10 power minus 3 over lambda max. Then you will apply rule R is equal to 1 over 2t square into square root of L over sigma pi. Thank you.